think it is live streamed, right, Dr. Divya?
Yes, ma'am. Yes, please proceed.
Okay. So good afternoon, everyone, to the weekly online lecture series on atmospheric dynamics and its applications to climate sciences, which is hosted jointly by South Asian Meteorological Association, SAMA, and Savitribai Phule Pune University. So today's lecture will be given by Professor Dr. SSVS Ramakrishna from Andhra University. But before we go to the lecture, I would request the Professor Someshwar Das sir to please deliver the welcome address.
Thank you, Dr. Rohini. AVM Dr. Tyagi Saab, President of SAMA, Professor Bhaskar Rao sir, advisory panel member of this lecture series, our other senior members like Bhatia Saab, and my good old friend Dr. Professor Ramakrishna, is honorary professor at Andhra University at present. It's very nice to see him here after a long time. Probably he's not attending any of our online lectures, so he may not be fully aware of what is going on. So I'll briefly tell about all that thing. But anyway, first of all, I welcome you all on behalf of the South Asian Meteorological Association and Savitribai Phule Pune University, India. As you know, this is the 11th lecture of the 5th lecture series on atmospheric dynamics and its applications to climate sciences. We started this lecture series on January, and it will go on till August. It's a 6.5 months course. Every week, one lecture. This lecture series syllabus has been designed based upon the feedback from the member countries of SAMA, and also based on the guidance of the advisory panel members of this lecture series. As you have seen by now, this 11th lecture, the first person or the speakers of this lecture series are all distinguished persons, senior scientists, senior professors. Many of them, some of them are also retired and honorary professors in their own university. As of last week, about 1,150 people from about 50 plus countries have registered for this course. Although on a typical lecture day, about 200 plus people attend live, and others are not able to attend live because of the time difference between their countries and India. But since the lectures are all recorded and available on the YouTube channel of SAMA, so most of them, they watch the lecture after it is over. So, and we can see that now the hits are increasing day by day for every lecture. The lecture series, as we have already mentioned many times, that is meant for MSc students, also BSc students, especially in meteorology. In some countries where it is available, like Nepal and Bangladesh. Also for those people who are interested in learning the subject and trying to work on the climate science. So this lecture series is also meant for them. This particular lecture series is slightly mathematical, but is very important for understanding the climate dynamics, atmospheric dynamics, and it is a prerequisite course for learning the numerical weather prediction in future, which will conduct a similar lecture series for about 5-6 months on NWP also. Because this lecture series on atmospheric dynamics and also the one which we had in the beginning on atmospheric physics are the basic two courses for learning the numerical weather prediction. Although we did have earlier a 3 weeks course on WRF modeling and its application with the help of CDAC, that you know, Center for Development of Advanced Computing in Pune. We also had hands-on training on the supercomputer of CDAC now through remote login. And we are planning a similar course also as certainly in future. But then they're all hands-on application mostly, not so much of theory on that. And theory will be taught later on in the NWP's lecture series, which we shall conduct later on. Okay, and we have already announced that we will give special certificates to those who have at least 75% attendance in this lecture series. And at the end of the lecture series, we shall conduct an online test, and grade certificates also will be given to all those who appear in the test and qualify as per their scores, like outstanding or excellent or very good, etc. Those grade certificates will also be given at the end of the lecture series. So I already know all the lectures are live streamed on the YouTube channel of SAMA. Okay, and so please ask your questions, whatever you have in the question and answer box, and it will be answered by the speaker at the end of his talk. So enjoy the lecture and have a good time. Over to you, Dr. Rohini.
Thank you, sir. Now I request Dr. Divya Prakash to introduce our professor and speaker today.
Good afternoon, one and all. Professor SSVS Ramakrishna is an honorary professor at Andhra University and the professor project manager of the Monsoon Mission at the Indian Institute of Tropical Meteorology, IITM Pune. He completed his MSc in meteorology with a specialization in numerical weather prediction and obtained his PhD in numerical simulation of tropical cyclones under the guidance of Professor D.B. Bhaskara Rao from Andhra University. His extensive international research experience, Professor Ramakrishna has completed 5 postdoctoral fellowships at prestigious institutions, including Florida State University, USA, the University of Paris, at the Laboratory for Dynamic Meteorology, Kyoto University, Japan, the International Center for Theoretical Physics, ICTP in Italy, and the Shannon Institute of Technology in Tokyo. His professional career has progressed from assistant professor to honorary professor, during which he has also held key administrative roles such as head of department, chairman of board of studies, and coordinator of the MOES Earth Sciences Technology Center. Professor Ramakrishna has attended specialized training programs under the aegis of ICTP Italy and has been the recipient of multiple scholarships and fellowships throughout his academic journey. He has delivered lectures for postgraduate students and has made significant contributions to metallurgical research. With approximately 80 research publications to his credit, his work continues to shape the field of numerical weather prediction, climate modeling, and tropical cyclone simulation, contributing to scientific advancement on both national and global scales. Thank you, sir.
Thank you, Dr. Divya. So now I request Professor Ramakrishna sir to please, he can share his screen and take the lecture.
Yeah. Thank you for your nice words about me, Dr. Divya and Dr. Rohini. Yeah. Are you able to see my screen?
Yes, sir, we
Yes,
can.
make it full.
Yeah.
Oh, yeah.
Yes.
Yeah. Thank you once again, all of you. I've been given the task of speaking on the kinematics of the wind field, and many topics were included to be covered here. Okay, I'll try to the best of my ability, I'll try to do some justice. Okay, so kinematics, as we all know, is that branch of mechanics concerned with the motion of objects without a particular reference to the forces which cause these motions, right? Okay, so in this first, we are supposed to learn about streamlines and trajectories. The word streamline is derived from the Greek word rio, which means flow, and streamline gives the instantaneous profile of a particle in a fluid flow. It's an imaginary line drawn in the flow field that is tangent to exactly to the velocity vector at any given point. The patterns of streamlines depend on the direction, magnitude, and the underlying terrain. Okay. Streamlines normally indicate the smooth curved flow, which visually represents the flow of air, with closer lines indicating areas of higher wind speeds or speeds and lines curving away from obstacles like mountains or buildings. The basic wind patterns which we are supposed to learn are: one is a uniform wind, in which streamlines parallel and straight and evenly spaced indicate a constant wind speed and direction over a large area. The other wind is the convergent wind, where streamlines converging towards a point, showing air flowing inwards with potential to create rising air. The other one is divergent wind, where we see streamlines spreading apart, showing airflow outwards associated with the sinking air. The other place where we find streamlines are jet streams, which are tightly packed with high-speed streamlines representing a narrow band, okay, moving very fast in the atmosphere, okay, often influencing weather patterns. We know about many jet streams in it. The mountain winds, upslope and downslope winds over a mountain, causing formation and bringing dry air respectively. So how do these streamlines look? For instance, streamlines are possible in both in a laminar flow as well as a turbulent flow. So these pictures above show the laminar flow, and the bottom picture will show you the turbulent flow of streamlines. Okay, and the other thing is the trajectory. The trajectory is nothing but the path attributed or taken by a particle within a fluid. A trajectory of a wind field refers to the path of the air over a particular time. Okay. So the wind fields, they do constantly change due to various factors like pressure gradient, temperature variations, and terrain. Okay, it is the differential heating, and then which causes the pressure gradients, and the pressure gradients result in flow of the wind. Okay, and here in kinematics of wind, we only study the movement of the wind without a particular concentration on the various forces that create these wind movements. Okay, what are the applications of these trajectories? Okay, the various applications are: one in aviation, which will help us to plan the flight paths and make an optimization of the fuel, especially in a commercial aircraft, by using favorable winds. The other is the pollution dispersion, to predict the movement of pollutants. Okay, in which direction a particular dispersion goes in the event of any accident or whatever it is. Renewable energy, to design the optimal placement of wind turbines. Okay, so this figure shows the flight of the trajectory under different conditions, like with no wind, with a condition 1 wind and a condition 2, whatever it is. So it depends on the conditions of the in space and tracing the point successfully anyway. Okay, so trajectory takes different courses under different conditions. Okay, what is this Balton's equation? Balton's equation gives essentially a relation between streamlines and trajectory. Okay, if beta is the direction of the wind or the curve at each point, if r suffix t is the radius of trajectory and r suffix x is the radius of curvature, the local change is given by wind multiplied by the curvature of the trajectory minus the curvature of the streamline. Essentially, if the trajectories are straight, okay, if the lines are very straight, what Balton's equations tells us is the steady conditions, these streamlines and trajectories coincide. Okay, that's how the equation is built. Okay, next, what are the four basic states of fluid motion? Fundamentally, they consist of four types, that is translation, vorticity or circulation, divergence, and deformation. What is this translation? Okay, so all these this picture shows the translation. Okay, picture B shows you the vorticity or circulation, and this is the divergence or convergence, and the fourth figure shows you the deformation. I borrowed from the Hess book, Theoretical Metrology, Introduction to Theoretical Metrology. Okay, forgive me for the quality of the picture. Anyway, so when you just dissociate the total wind, it consists of many terms. That is translation, the divergence, relative vorticity, deformation in two components, that is stretching deformation and shearing deformation. Any wind field that varies linearly can be characterized by the above five properties. Okay. Now, what is individually this translation? Translation is pure straight motion. Okay, it could be in a steady flow or a non-steady flow, where the difference is between steady flow, the speed is uniform, and in a non-steady flow, the speed changes from time to time. Okay, and it is the movement of a fluid element from one position to another without any change in its shape, size, or orientation. Okay, okay, it is a kind of a motion where the individual fluids simply move in a straight line. Okay, now this is how the translation looks like. Okay, so this first term in both the equations, they represent the translation. The effect of translation on a fluid element is shown in this figure. For instance, there will be only a change of location, okay, but no change in area or orientation or in shape of the fluid element in a pure translation. Okay, this is how translation affects an individual particle in a fluid. The next one is the divergence or convergence. Okay, the expansion of spreading out of a vector field, which otherwise called as negative divergence, that is convergence. Okay, its counterpart, and it is given by the del operated by the on the vectorial wind, del dot v. Okay, mathematically it is given by dou u by dou x plus dou v by dou y, but in the full form it has got dou w by dou z. For all practical purposes, we only consider the horizontal divergence or component of the divergence, neglecting the vertical component. Okay. What are these terms? See here, dou u by dou x plus dou v by dou y is the divergence. Okay, and the effect of convergence or divergence is given in this figure. Here it is the case of convergence. Okay, and if it is diverging means the small square would become a larger square, kind of. Okay, change in area. Okay, no change in the orientation, again shape and location. Okay, this is how the effect of convergence is there on a fluid element. Okay, what are the applications of these divergence and convergence? The convergence means into a column of the atmosphere, it brings in more air, leading to ascending of air, and which should be automatically compensated by a divergence aloft in order to satisfy the equation of mass continuity. Okay. Likewise, if there is a divergence at the lower levels, okay, it should be compensated by a convergence at the upper levels, and this results in sinking motion, okay, downward motion. Okay, let me spend the time about the continuity equation and the vertical motion here. When you consider the continuity equation, it full form reads as dou rho by dou t is equivalent to, d rho by dt is equal to dou rho by dou t plus u dou rho by dou x plus dou rho by dou y plus dou rho by dou z plus rho into dou u dou x plus dou v dou y plus dou v dou z. When you impose the condition of incompressibility, only the last term remains, that is rho into dou u by dou x plus dou v by dou y plus dou w by dou z, which gives, that is del dot v is equal to 0. Okay, this is the full form anyway. So this indirectly gives you that the three-dimensional divergence or simply the two-dimensional horizontal divergence, okay, it can be equated to like this, del dot v. So if you take this dou w by dou v to the other side, the horizontal divergence can be estimated by indirectly from minus dou w by dou p here. Okay. So this is the equation essentially states. If you take p coordinate system instead of the z coordinate system, this is how the equation looks like. Omega is the vertical p velocity, and it gives, at a given pressure levels, it is proportional to the integral of the divergence or convergence above a given pressure level. Okay, so this vertical velocity is related to the horizontal divergence. Okay, now the convention is that if you take the z coordinates, positive upwards and negative downwards, while when this is in the p coordinate system, okay, when vertical velocity is negative means rising motion, okay, when it is positive it is called subsiding or sinking motion. So this rising motion is, yeah, divergence aloft and then, okay, convergence at the lower levels, and this is convergence aloft and divergence at the lower levels. Next comes vorticity. Vorticity gives you the circulation, is defined as the infinitesimal rotation of an air molecule around its own axis. Only it is around the z-axis we normally take the vorticity. It is measured by the formula dou v by dou x minus dou u by dou y. Okay. And let us see how the vorticity affects the fluid element. Right. So this is the vorticity term. Okay, dou u v by dou x minus dou v by dou y. Convention is positive vorticity is likewise cyclonic, and negative vorticity is anticyclonic. So the effect of negative vorticity on a fluid element is seen like that. You will see the whole orientation will be tilted toward change in orientation, no change in area, shape or location. Okay, this greenish blue will become the pink one. Okay, if you have a negative vorticity. Now, vorticity, which is, as I said, spin around a vertical axis, okay, comes from three sources. Whether it is a sheared flow like this, a curvature flow, and the rotation of the earth, okay, which is given by F. Okay, shear and curvature gives you this, and absolute vorticity, which is zeta plus F, is nothing but the vorticity plus F. In the tropics, you consider the relative vorticity plus F, that is the Coriolis parameter or the Earth's angular velocity, and if you calculate the F value in the tropics, F normally is of a lower order than zeta, that is dou v by dou x minus dou y. So hence in the tropics this is very important. But when it comes to the extratropics, the zeta plus F takes the form of 10 to the power of minus 4 of that order, and your vorticity still remains in the order of 10 to the power of minus 5. So in the extratropics, if it is the F that dominates, while in the tropics, it is this component that dominates. Okay, what is next one is, last one is the deformation. The change in shape of a fluid mass by spatial variations in the vector field, especially by stretching or shearing. So deformation consists of stretching deformation or shearing, shearing deformation. Okay, this deformation essentially leads to the formation of fronts. Okay, now this is the stretching deformation term. Okay, dou u dou x minus dou v by dou y, and the effect of deformation can be seen in this picture. The effect of stretching deformation on individual fluid element. Okay, so only change in shape, no change in area, orientation, and location. Okay, the axis still remains in the same part. Okay, place. Next one is the shearing deformation. Okay, so when you have a shear, deformation also makes the fluid element in this way, something like a square or a rectangle to a rhombus. Okay, this is the angle of the shear strain. Okay, the more will be your shear strain, the more will be the orientation. Okay, from a rhombus into like that shear strain. So this is how the shearing deformation looks like. Now, deformation flow is fundamental to the development of fronts, as I said. Okay, this is the two axes of the fronts, and sometimes this point is called the call point anyway, and this is how the deformation will be there in the form of fronts. Now, pressure tendency equation. Okay, to derive the pressure at a particular point, we shall start from, okay, begin with the hydrostatic approximation, dou v by dou z is equal to minus 0. If you integrate this equation from the surface z is equal to z0 to a height z is equal to infinity, okay, so minus 0 dz. Okay, so since at the top of the atmosphere pressure becomes 0, okay, this will be P is equal to Z0 is equal to Z to 0 to infinity into 0 dz. Now, if you differentiate both the sides, okay, you will get this equation. Okay, again, from the continuity equation, you will get dou rho by dou t is equal to minus del dot rho v. So you have three terms here. Okay, the pressure tendency equation consisting of three terms, that is the divergence term, the net advection of mass, and the flux from its base. When there is a net inflow of air in the form of convergence, will lead to rise in pressure, and divergence lead to fall in pressure. The second term in the pressure tendency equation represents the lateral advection of mass. Okay, this term. And the third term is the mass flux into the above atmospheric column. These two terms are very difficult to measure. Hence, normally we only consider this part of that is the divergence term in estimating the pressure tendency. These two are very difficult to measure. Okay. Now, coming to the ridges and troughs. Okay. This is a ridge, locus of maximum negative curvature, okay, and a trough axis or a trough line locus of maximum positive curvature. Okay, this is this dashed line. Okay, is the trough axis. If the axis is oriented normal to the trough axis, then along the ridge, dou b by dou x will become 0, and your second order will be greater than 0. So intensity of the trough is given by dou square b by dou x square. And here is an example of a weak ridge where the isobars are placed, okay, with larger distance between them. Here is the case of strong ridge. Okay. Now, how do the tilted trough looks like? This is a positive tilted trough in the westerlies, and this is a negative tilted trough in the easterlies. Okay. Yeah. What about these high-end pressure centers? A high pressure center for a high is a local maximum in the pressure field. At the center of the high, there will be divergence leading to sinking of airflow. Okay. So here, this is the high pressure, and away from the center, the pressure would be low. So the pressure gradient will be away from the center, and as per to the Bias-Ballard's law, towards the normal of the pressure gradient force, your wind vector would be like this. Here, the wind would be like this. Here, the wind would be like this. Here, it will be like this, and then. So, around a high, the motion would be clockwise here. Similarly, here, around a low pressure center, this is the high pressure area. The pressure gradient force will be in this direction, and towards the right in the northern hemisphere, the convention is in the northern hemisphere, towards the right, the wind vector would be here. The wind will be like this. Here it would be like this. Here it will be like this, and here. So it is a anti-clockwise or cyclonic flow. The low pressure centers are always associated with rising air, okay, and the rising air expands and resulting in some rain. So around the low pressure area, winds would be not only strong, anticyclonic, and also they give rain. But around the high pressure area, the winds would be cyclonic, sinking motion, but there is no rain. Okay, subsidence will be there. Now, so this is an example of in this first picture, this high nearby propagating towards the observing station. Dou p by dou t will be greater than 0 in all these cases. There is a low nearby which is going away from the observing station, and this is again a high pressure area, okay, which is building up, and here this is a case of a low pressure area. Okay, so all these arrows, they indicate the motion of the isobars. Okay. Now, illustration of the relationship between the motion of a ridge and the temporal and spatial variations in the pressure field. If an observer is to the right of the ridge, isobars are being given by these solid lines. Okay, he will observe a local pressure rise, and an observer is to the left of the ridge, notes a pressure fall. Then the ridge will move from left to right. Okay, in this case, I would like to spend some more time here on the concept of vorticity. Okay, the vorticity, I think the full form of the vorticity equation takes many terms. I think it's beyond the purview of this lecture. The vorticity equation consists of a divergence term, a tipping and a tilting term, plus a solenoidal term plus a frictional term. Okay. And for all practical purposes, I think again we take the divergence term into consideration. Okay. Now, once again, just to spend some time on this divergence concept. Okay. Yeah. This as I said, it is the convergence, which is automatically compensated by an upper level divergence. Once again, yeah, this around a cyclone will send in lots of mass of air, bringing in air, which again rises, and then it should be automatically, I think the arrow should be the other way, the automatically compensated by divergence. So around a low pressure area, yeah, as I said once again, it is the rain that is associated with low pressure areas, while with the divergence here, it is the only the sinking motion of the air. Okay. I think 1 minute. Yeah. Yeah, I think I'm falling short of slides anyway. I'm sorry, I don't know how much time did I spend on this. Okay. Uh, yeah, I think that's it for now, anyway, from my side. And yeah, I'll be very happy to answer the questions given by, posed by the students. Okay. I might have done a quick job. I think maybe, did I spend half an hour at least? I don't know.
Sir, if you want, you can complete the slides also. I mean, the remaining one.
Yeah, I don't have any more slides away. Yeah,
Okay.
this is my last slide. Okay.
Okay.
Yeah. I'll be very happy to answer questions.
Okay.
I think I was a bit too fast on this explanation. Yeah.
Okay, sir, before we go to the question answer session, we would just take a picture, all of us together. So I request all the panelists to please switch on their cameras. Sir, I request you to please unshare your screen for some time.
Yeah. Stop chasing the share. Huh? Chasing.
Tyagi sir, Das sir, Bhatia sir, Dr. Divya, Dr. Mohan. Dr. Divya. We'll take another picture probably later. Ashwin, can you take? Okay. So now I request Ms. Mrunal Naik from IITM Pune to conduct the question answer session.
Thank you, ma'am. Thank you, sir, for the wonderful lecture. There is a question from Josel. He's asking, can you please explain how vertical velocities are related to convergence and divergence that occurs at the surface of air, and how this corresponds to rising and sinking motion?
Can I share my slide now?
Yes,
Yes,
sir, you
sir,
can.
yes.
Yeah, for instance, imagine that this is a low pressure area, okay? And in the low pressure area, at the lower levels, there will be some convergence. This converging air, in order to satisfy the equation of mass continuity, it should go high up, rise, and then go out on the vertical column in the form of divergence. Okay, this convergence, okay, will lead to rising of air and how the vertical velocities are built up. Okay, this is indirectly given by the magnitude of the convergence, that is minus dou u by dou y of dou v by dou x. That is negative divergence is equivalent to the proportional to the rising air, that is the vertical motion. Okay. Similarly, for high pressure also, for sinking motion also, the same concept holds good, of course, in an opposite direction. Okay. Am I clear in answering this question? Or
Sir, yeah, that's
Yeah.
good. Yeah.
I mean,
Yeah.
is it okay if we interact with the students there? No.
Sir, we won't be able to because they only type. Yeah.
Okay, fine.
Yeah, so that's it, sir. There are no more questions
Hmm.
by the students. Okay, sir, there is one question by Dr. M.G. Manoj. What does the negative sign in relative vorticity signifies? Does it signifies du by dy? To be more specific, his query is simple to calculate du by dy and to add it to dv by dx.
Even in the vorticity, he means?
Like negative signs in
Yeah,
relative
relative
vorticity.
vorticity. Yeah.
Huh?
Yeah, sir.
Yeah.
Negative sign in relative vorticity. Yes.
I mean, it is a convention in the northern hemisphere, cyclonic, okay, anticyclonic means positive vorticity, right? Okay,
Hmm.
and negative vorticity is clockwise. Okay, that is the convention used. Positive vorticity means anti-clockwise, that is cyclonic flow in the northern hemisphere, and then negative vorticity is clockwise. Okay, is that
Yes,
okay?
sir.
Hmm.
Hmm. So there is another question by Deepak.
Hmm.
He's
Yeah.
asking, low pressure at lower level causes convergence and it causes rising air and then diverges at higher level.
Yes.
What determines at which level the divergence will happen?
See, so this is the converging air, okay? That is negative divergence. This is positive divergence. Somewhere between 600 and 500 millibars, there will be some level of non-divergence, okay? And your divergence will be predominant from 200 hectopascals and above, okay? So 600 to 500, there will be a non-divergent level from where this negative sign will slowly from zero. This is the where zero will be zero. From here, it will be slowly becoming positive. Okay, predominantly at about 200 hectopascals, the divergence would be more.
Thank you, sir. So,
Yeah.
there are no more questions.
Hmm.
Yeah. So I conclude the question answer session as over.
Yeah. Thank you, Mrunal. Before going to vote of thanks, I would like to tell the statistics. So around 111 participants have registered their attendance, out of which 95 participants have rated this lecture as excellent or very good. So though it is equations were there, it is a really nice and impressive lecture, sir. Now I request Mr. Ashwin Zadav from SPPU Pune to please give vote of thanks.
Thank you, madam. Sir, can you please unshare your screen?
Yeah.
I can. Yeah. Thank you. Thank you, sir. So on behalf of organizing committee, I extend my sincere thanks to everyone who contributed to the success of the 11th lecture in our weekly online lecture series on atmospheric dynamics and its applications to climate sciences. We are especially grateful to Professor Someshwar Das, Secretary SAMA, for his warm welcome address and insightful overview of this lecture series. My heartfelt thanks also goes to our distinguished speaker, Professor SSVS Ramakrishna, Andhra University, for delivering an enlightening lecture on kinematics of wind field, Balton's equation, Trough ridge, and their equation with interpretation. So I would like to acknowledge Dr. Divya Prakash for introducing our today's speaker, Dr. Rohini Bhavar for moderating the session, and Ms. Mrunal Naik for efficiently managing the question answer segment. Additionally, I appreciate the guidance and support of all the panelists and listeners. A special thanks to all the participants and attendees who joined us from across the globe, and to the dedicated team members at Savitribai Phule Pune University for their valuable role in organizing this lecture. Thank you all.
Thank you, Ashwin. Okay, Someshwar Das sir is here. So I think we will take one more picture.
Yeah.
I request everyone to switch on their cameras again.
Okay, okay.
Yeah, I think this is perfect now.
Yeah, Bhatia sir. Ajit Tyagi sir.
Madam, you are not visible.
Yeah.
I thought there was some technique.
Okay.
Yeah,
I
now
will
we can
yeah.
take. Yeah.
Yeah.
Thank you.
So around, sir, you were not there probably for the statistics. Around 124 participants have registered there, and 100 or more have given it as excellent or very good.
Okay, great, very good. Thank you. There is a holiday sometime later, Eid or Bakrid.
Yes, sir. Yeah.
Maybe not now, maybe sometime in June.
I think we have considered that. Yeah.
Okay, okay.
We have kept a blank slot probably that time.
Yeah. So next lecture
Will be by Professor Suresh C.A. Babu, sir.
C.A. Babu from Cochin University.
Cochin University, yeah.
Okay. Fine.
So we can stop live